What's up guys, it's me Sir Ernest, and today we're going to solve a problem involving capacitors and inductors. The problem reads, a capacitor C is charged up to a voltage V and connected to an inductor as shown schematically in figure 7.39, which I'm going to draw later. At time equal to 0, the switch is closed. Find the current in the circuit as a function of time. How does your answer change if a resistor is included with the capacitor and the inductor? Okay, so this is how 7.27 look like. So you have your inductor here, and then you have your switch as here, and then on this side you have your capacitor. Okay, so as mentioned here, the capacitor has a voltage, is fully charged with a potential difference of V, and that is connected to our inductor L. Now, at time equal to 0, the switch is closed. Okay, so when the switch closes, okay, current will now flow through the circuit. Now, to find the current in the circuit, let us first find the initial EMF. So the initial EMF E, which is equal to V, is equal to the charge in the capacitor Q. So let's say that's Q divided by the capacitance, and this is also equal to L, that negative L, that's the inductance, times the derivative of the current with respect to time. And we know that the current I is just the first derivative of the charge with respect to time, so we can rewrite this term as negative L times the second derivative of the charge respect to time, and we're looking for this Q. Okay, so combining this, we now have second derivative of Q with respect to time plus Q over LC, or 1 over LC times Q equals 0. So what do you notice here? This equation resembles a simple harmonic motion equation. Okay, as you can see here. So therefore, we can rewrite this second order differential equation as second derivative of Q with respect to time plus the square of a angular frequency omega times Q equals 0, wherein here we define omega squared to be 1 over LC, and the solution to this equation is Q, so function of time, and that is equal to A cosine omega t plus B sine omega t. So applying our initial condition that at t equal to 0, E is equal to V, and Q is equal to CV. Therefore, Q at time equal to 0 would be equal to A cosine 0 plus B sine 0, which is equal to CV. Because sine 0 is 0, therefore A is now equal to CV. So therefore, we can now rewrite this equation as Q as a function of time equals CV cosine omega t plus CV cosine omega t plus B sine omega t. Now differentiating this with respect to time, and that will give us the current. This gives us negative omega CV sine omega t plus omega B cosine omega t. Now let's apply again another initial condition, wherein initially, because there is no current flowing when the switch is still open, so that means upon closing the switch, that's time equal to 0, there is still no current flowing through it. So using this, we can now use this initial condition in this equation. So that means I at time equal to 0 is negative omega CV sine 0 plus omega B cosine 0, and this is equal to 0. So sine 0 is 0, cosine 0 is not 0, so therefore B is equal to 0. So therefore, finally, the current as a function of time can now be written as negative omega CV sine omega t, or negative V times the square root of C over L. So this omega CV is negative V square root of C over L times sine T over square root of LC. So you will notice that the current is actually following a sine function. Okay, so the current will flow alternating. So this is an alternating current. Now what happens when we have for example, if we add a resistor in the circuit? Okay, so if we have a resistor, our circuit will now look like this. So this is your inductor, this is your resistor, and this is your capacitor. So this is now an RLC circuit, and let's say the switch is closed. Okay, so by Kirchhoff's loop rule, the total charge, the sum of voltages in this loop will now be equal to E. So that's the voltage or the EMF in the capacitor plus IR, so that's the voltage across the resistor, plus L, derivative of I with respect to time, that's the induced EMF in the inductor, and this is equal to 0. So expressing everything, all the I's in terms of Q, so this will now be written as L times the second derivative of Q with respect to time plus R times the derivative of Q with respect to time plus 1 over C times Q equals 0. So how do you notice, what do you notice here? So you can see that this equation is non-simple harmonic. Okay, in fact, this resembles a damp oscillation. Okay, so physically what happens here is, as you will notice again here, that the current, if you only have current, capacitor and inductor, the current will just flow back and forth by this behavior, and it will continue forever. Okay, because neither L nor C will use up the energy. Now, because we have, in this case, we introduce a load. So just like your appliances, this load uses up the energy, uses up the charges, uses up the current. So as the charge goes back and forth in a oscillating manner, okay, this resistor uses up that energy given by P equals I squared R. Okay, we call this your Joule heating. Okay, so energy is dissipated in the resistor, thereby slowly decreasing the amount of current flowing through the circuit. So if we're going to graph that, it would look something like this. It would look something like this. So this is a damp oscillation. Of course, this is just a sketch. So you can actually calculate the charge as a function of time by referring to your lessons in your theoretical mechanics or classical mechanics. Okay, so that's it. So that's what happens if a resistor is included in the LC circuit. Okay, so with that ends our solution to problem 7.27. Thank you guys for watching. I hope you learned something, and I'll see you guys in the next video. Bye bye.